Can you give us your name and your affiliation?
My name is Esteban Gazel. I am a professor at Cornell University in the Department of Earth and Atmospheric Sciences in the College of Engineering.
Fantastic. And what does your work involve?
So I study volcanoes for the most part as probes to the deep Earth. Um, Volcanoes are the only way we can access the deeper parts of our planet. So we want to understand the evolution of the planet, its relationship to other solar system bodies that are similar, and all the different layers of the planet and how they interact with each other. The only samples to the deep Earth are accessed through volcanoes. You can imagine them as these really deep boreholes that bring materials from the deep Earth. So my career has mostly been focused on understanding geochemical reservoirs inside the planet. And over the last few years, I started applying some of these tools that I started applying some of these tools to understanding volcanic processes.
So can we just start with that?
Yeah.
So over the last few years?
Yes. Over the last few...
Don't worry.
Okay. Over the last few years, I have been moving in the direction to applying some of the tools that we use or we generally apply to the mantle processes to understand how volcanoes work and what are the mechanisms behind the eruptions. So my lab at Cornell is specialized in the study of volatile contents in volcanoes.
So the stuff that flies out of...
Yeah, basically volcanoes are explosive because they have water and CO2. And also because they have polymers of silica. The most silica you get, basically, yes, sorry.
I was just going to say, because everyone else is on silent.
Mine's on 3G, on airplane mode.
Yeah, okay, let's kill this.
Okay.
So volcanoes are explosive, I guess.
Yes.
Volcanoes are explosive because they have high silica content, and that make polymers, increase the viscosity, and it keeps the volatiles inside. Volcanoes can also be explosive because they have a lot of water. So when you think about water and volcanoes, it's like fire and water. You cannot put them together generally. But what makes a volcano very explosive is water and CO2 contents. And during this work of understanding volcanic eruptions, we also discovered that fractions less than 1 micron are hardly studied. Generally, like in our field of research, we study fractions or samples from what you get in your hand to whole volcanoes to, maybe to a couple of microns. And it mostly has to do with the analytical limitations of some of our tools. But we can do really well in some instruments like transmitting electron microscope or TEM. With those instruments, we can go beyond 1 micron, or with scanning electron microscopes. And we wrote a proposal to NASA to integrate atmospheric science with satellite monitoring of volcanoes and trying to understand what is the impact of this very fine-grained fraction that is one of probably the one that is going to affect the planet at the global scale. The most, like, you could be very far away from the volcano. You're reading the newspaper, drinking a coffee, and breathing particles that came from a volcano many, many miles, hundreds of miles away. And that could be something that can directly affect people. We know that volcanoes have an impact on the Earth system by increasing productivity in the ocean because there's iron, and especially like the eruption like this, it will have a lot of iron. That iron is going to go into the ocean, is going to increase productivity.
Sorry, what do you mean by increased productivity? What's the impact of that? What do you mean?
Basically, there are microorganisms that live in the ocean that start the chain of productivity. Like basically, they need iron to exist. And that iron is going to be coming from the volcano. So when these particles are spread in the ocean, they will give more nutrients like iron and phosphorus to the ocean, and that will produce a bloom of organisms. So we're trying to understand what is what is the effect of these tiny particles in biogeochemical cycles. And the other dimension of this project is the impact on climate.
And all of this study is being backed by NASA, yes?
Yes, this is supported by NASA.
So just to put it in very, because I find this fascinating, because obviously a lot of people are talking about the destructive nature of volcanoes, but there wouldn't be life without volcanoes, right?
Yeah, having volcanoes is probably one of the requirements for habitability in a planet.
Why?
Because volcanoes recycle the atmosphere. Volcanoes produce the atmosphere. Actually, there is a say that the atmosphere of a planet is a combination of life and geology. And from that, volcanoes is one of the most important players, because all these volatiles that I'm talking like water, CO2, etc., nitrogen, come through volcanoes. You are breathing today air that once came through a volcano.
That is beautiful. So why did you decide to come to La Palma?
We decided to come to La Palma because is the opportunity to sample during an active eruption is rare, but it's even more rare to have the opportunity to do this work in a safe environment. I think the authorities have done an excellent job. The volcanoes were really well monitored. We know when is the forming. We know when the earthquakes are happening. If something is happening when we're in the restricted area, they will take us out of there. And again, like the fact that we can collect samples in real time during the eruption from the source all the way to distal areas give us a really good information that is not going to be possible to do it later.
That's really interesting. So just talk us through the actual work you've been doing in, what's your typical day in the exclusion zone here in La Palma? What have you been doing?
So in the exclusion zone, what we did is that we sample all the different layers. So we went to a part that has not been disturbed. We took a shovel, we dig, and we were able to sample every possible layer up to yesterday. And we're going to take those to the lab, and we're going to do different studies there. We're going to analyze their chemistry, the minerals, and hopefully we have interesting minerals. We can also eventually get the volatile contents through the glass inclusions. The other thing we're doing is that we're sampling particles directly from the air. So we have an instrument that 30 seconds, it sucks air. It's called a cascade impactor. And then that goes into 3 different chambers of 3 different grain sizes. And the last chamber has the possibility of sample the nanoparticles. And what is really cool about this instrument is that it deposits directly into the stuff we take to the electron microscope. So we take all these little samples that are already ready to go to the microscope. So once we get back to Cornell, we can go to these different electron microscopes and start collecting data of the tiniest particles. And we did that all over the island, from very close to the vent during ash falls all the way to the observatory, the astronomical observatory. So we can have a good background of what is the air without the volcanic materials.
Well, you say a background of air without volcanic materials, but they've had to shut the world's greatest telescope down, haven't they, because of the ash in the air, and they're worried about that getting into the mechanisms and onto the...
Yeah, every so often there is actually there is a bucket there from the folks from the University of La Palma of Gran Canaria, and every so often when the upper winds are right, they take ash in that direction. Yesterday they were going the other way, so we were able to get a background, but every so often it goes there. There is record of ash falling all the way to the island of El Hierro when the plume was 6,000 meters. So that's just a testament of the fact that these materials can be transported very far away, especially the sizes that you don't see.
So you came here all the way from the States to La Palma. What happens here in La Palma has an impact globally, we're saying. What impact might it have?
Well, the global impact will depend on many factors. The eruption size, its composition, the exsolution of gases, where in the planet is, and you can say that all eruptions will have some level of global impact, even the really small ones. But we probably have not up to this point understood so far what is going to be the global impact of this eruption until we have more data in the future globally. But it's a good test bed, basically, of how an eruption of this composition will act. And what we can do is could potentially use the data we have here and scale it to an even bigger eruption.
That's really interesting. And could it have an impact on climate change, for example?
What volcanic eruptions do, it's a little bit difficult for me at this point to answer that question. But what big eruptions do is that they cool the planet for a few years. If you put enough sulfur and ash particles in the atmosphere, there are some historical eruptions that had basically impact climate globally. So it will cool the temperature for a couple of years. Some of those eruptions are like Tambora or Krakatoa or even Pinatubo. So they are different eruptions compared to this. It's completely different, remember? But they have affected climate up to the point that some of these eruptions, we were not able to produce food in the northern hemisphere for a while. There were snow lines all the way to New England in June. Probably the worst world crisis we can experience is a Tambora style eruption again. Imagine what will be all these natural sounds.
Yeah.
And unnatural.
Muppet in his souped up 1 litre Ford.
Yes, exactly. With the exhaust taken off, so it sounds better.
Okay.
And his friend.
So the worst thing that could happen would be another
Tempura.
Yeah,
So the worst thing that can.
If I don't use grammar properly, please tell me, because I
worry.
make a mess.
No, it doesn't matter.
And it's a
Because
little
you're not
embarrassing.
It's not your first language.
But A, it's not your first language, so nobody's going to judge you on that. And B, what's fantastic is your passion and your energy and your knowledge, and that's what we're interested in. You know,
Okay.
I'm dyslexic. He's dyslexic.
I'm
You know,
dyslexic.
I go on
All
social
geniuses
media.
are.
Yeah.
Yeah, no,
I go on social media.
I'm pretty bad.
But it doesn't matter, honestly, because
Without computers, I don't know how successful I could be, because it's
Right man,
difficult.
right time. The
Yeah.
world was waiting for you, don't worry.
yeah.
Just relax your arms.
Okay, so
So we're
So,
clear.
the worst that could happen. Oh, hang on a sec. Are we rolling?
Yeah, it's just a volcano, which is good.
Excellent.
yeah, so I think I strongly believe that one of the worst crises humanity can experience is a Tambora style eruption again, given the way the global economy is all connected, and a significant amount of wheat, soy, corn is produced in the northern hemisphere, and this is the global production. And some of these eruptions, as I mentioned before, triggered this global cooling for a few years. That there was, there was snow covering all the way to New England in the United States, all the way to June. One of these eruptions triggered the year without a summer, and without producing food for a year or two, I think we're going to be in a lot of trouble. If you look at some of the biggest human historical events, like the collapse of the Roman Republic, or even potentially the French Revolution, they're all related by eruptions that cause some kind of global impact.
There's a volcanic explosivity index. And
Yes.
It goes from 1 to 7. Is that right?
So, to put eruptions in perspectives that they can be compared, there is this index called the volcanic explosivity index, and a very mild eruption will be a 1, a really big eruption will be 7, and that will be a super caldera eruption in Yellowstone will be like around 7.
So this
And-
one here would be a 2 or a 3, I think I've read. Is that right?
Yeah, it's probably no more than that. But it's not just the volcanic explosivity index that will affect climate. It's how much sulfur you can put in the stratosphere. So there are basaltic fissure eruptions like this that happen in Iceland. More volume than this. Again, we don't know how long this is gonna last. We don't know for how long it's gonna go. But a basaltic eruption can also put a lot of sulfur in the atmosphere, and you don't need a Pinatubo or a Tambora style eruption to also affect climate. You just need the right amount of sulfur. And basaltic and hot eruptions like this have a higher potential of carrying sulfur. So we don't need the scale of Tambora or Pinatubo. They could be not so huge, but they can bring more sulfur. So again, it's a matter of that balance between how much you put out and the potential of bringing sulfur as part of their contents that are degassing as they come to the surface.
And do we know how much sulfur this one's putting out?
No, I don't. I'm pretty sure there are measurements done already of how much sulfur is coming out, because there is. I know the colleagues from Italy that are some of the best that they do the multigas. They have put a series of instruments. You can see some of the sulfur with satellite too, but they need ground truthing with the instruments on ground. What I could give you eventually is the pre-eruptive sulfur content when we measured that in the lab. So a combination of the field studies and the lab studies will give us the sulfur budget. So it's going to take a little bit of a while to get the total sulfur budget.
Okay. So if we could just have a quick phrase of you saying, in terms of size and scale, in terms of explosivity and damage, this is a 3 compared to a 7.
In terms of damage, well, it's gonna damage the infrastructure down the way of the lava flows, and some houses are gonna be affected by the pyroclastic material more than others. But again, they have done an excellent job evacuating people, so hopefully we're not gonna lose anyone here.
So that leads into a particular field of interest of mine, is how this is reported, because you have Pevolka, which I think is doing a great job at sort of coming together with all the various institutions and putting out a press release every day telling people what's going on. But from the outside, sometimes what gets into the news or onto social media are very close-up shots of this volcano, and I have family members, for example, who think that my life is in imminent danger at all times working here, because they see this sort of ball of fire going up into the air and they think I'm sitting under it constantly.
So I think the best way to understand a natural emergency, like anything from a volcanic eruption to an earthquake to a hurricane, is to listen to the authorities, the experts that are in charge of handling the crisis, rather than other people that's not their job.
And that's the same across any scientific
anything.
field of science. Yeah,
Yes.
Exactly. So obviously people's safety is of paramount importance in all of this, and keeping people safe, and the authorities have done a great job at keeping people away from the exclusion zone and setting up a perimeter. But what strikes me as well is that there's a lot of people within the exclusion zone working, and I wonder if they all are working safely.
So all the time, I can only tell you what was my experience when I was there. Every time that you're there are a lot of, we have police and volunteers and Guardia Civil, and all sorts of, authorities everywhere. So they're constantly monitoring, they're constantly asking for our permits. And I will imagine that if they get the news from the authorities that are monitoring the emergency that they need to evacuate everybody, we probably can get out of there fast.
So we had an eruption here in 1971, which was quite different to this one because it was much closer to the coast and the lava just ran down towards the sea.
Yeah.
But we did have 2 deaths related to that eruption. And one was somebody who got too close to take a photograph, and somebody else was somebody who would visit the eruption frequently and was eating the grapes locally and actually died from the poisoning from eating the grapes. And the thing that strikes me is that we are seeing on social media, for example, a lot of scientists taking selfies, and they might not have their gas masks on, and they seem to be very close. Does that give the right message of, you know, let's still be respectful? This is a dangerous volcano, and we need to still be careful, or just to say, look, aren't we cool?
I think we are guests here, and we need to be part of the solution, not part of the problem. So I can only tell you for what our team did, and we were always following the rules. So we always had our mask on when we were in the exclusion zone. We had our helmets, and pretty much we follow all the rules.
What masks were you wearing?
We have two types of masks. We have masks that cover your whole face and has two respirators that are good for particulate matter, and they also protect you from acids. They're good for 40 hours, so in 40 hours you replace the cartridges. Then we have some other masks that cover your mouth, and they're the same principle. They basically will have some chemical reaction in the mask that will protect you from the acids.
So I just want to put that into context, because people will wonder why, for example, the authorities are saying, you know, an FFP2 is okay for the population, but then maybe they see the scientists with these other gas masks on. So it's important to explain, if you're a scientist working next to the eruption,
Yeah.
why do you need these face masks? So if you could start with that. If you're a scientist working really close to the eruption, you need these gas masks because...
Well, you need it because you're going to be there
Sorry,
for a long...
if you could start by saying, if you're a
Okay,
scientist...
so if you're a scientist and you're close to the eruption site, you are at a higher risk. If you are like in the restriction zone, you're at a higher risk of being exposed to sulfuric and sulfuric acid and chloruric acids coming from the eruption. It's basically once the lava comes out, all these gases separate, and when those gases separate, they interact with the atmosphere and they produce acids. So you're gonna breathe them, and then you're gonna get in trouble. Not necessarily you're gonna die right away, but you could be in a lot of trouble. And it's like with chemistry, it's all about doses. So if you're gonna be there all day long, you need to be careful by having one of those masks. Now, if you're here and suddenly you have an ash fall, you need a mask that will protect you from the ash. We're far away enough that the concentration of those gases will be, you can still smell them, but it's again, chemistry is all about concentration. The closest you are to the source, the most danger you're gonna have. The most those materials get dissolved, the least of a danger for the general population.
That's an excellent explanation, because the population here have seen online pictures of scientists who perhaps have taken momentarily their mask off to have a quick photograph, but that doesn't mean to say it's safe for them. We have had incidences, unfortunately, of people sort of diving under the exclusion zone barriers to get their own selfie, and it's not safe for them to be doing all of that without the proper equipment covering it.
Well, and also, like, they are not connected to they don't have their names, they don't go through the process, they don't have their phone numbers. Like, when you enter the restrictive area, they have all your information. So if there is an emergency, they're going to give you a phone call right away. They will get you out of there right away to try to avoid more any potential issues. If you go to the restricted area without the proper permits and everything, then you're at the risk that if something bad happen, you're not going to know.
That is excellent, really good. And as well, the emergency services have been working incredibly hard under very difficult conditions to keep everybody safe. And actually, by people going under these barriers, they're putting them under unnecessary additional pressure as well, aren't they?
Yeah, I think it's very selfish. You can take nice pictures from a safe distance. Volcanoes are very dangerous. They're really high temperature, they're really unpredictable, they have a lot of power. And not just the fact that you can get impacted by a bomb that is partially molten. It's just the fact that the concentration of gases.
Big rock.
Big molten rock. Well, it could be from like a few centimeters to the size of of a pickup truck
Flying through the air.
Yes, there is a record, I think, at Arenal volcano in Costa Rica, when I'm from, that at 5 kilometers, a piece of molten rock came from the volcano 5 kilometers away. Now, that was a very, very aggressive eruption. It's not what we have here. But again, volcanoes can be very unpredictable. If you are within the restricted zone, that means that you are in danger and you need to follow the rules.
And how far could this eruption throw projectiles?
It's a little bit difficult to make that prediction.
But
looking at what is happening right now, it looks that the projectile ejecta is restricted to the area that they don't allow people in, that is within a kilometer of the volcano.
and does that include scientists aren't allowed in that area?
Yeah, not even scientists are allowed there. Yeah, there is like a 1 kilometer radius around the cone right now that no one is allowed. The basic rule, we're not allowed. Yeah.
That's really good. And just finally, I wanted to touch on the area of collaboration, because obviously there's a lot of scientists here working for different institutions, and on the one hand, there is an element of competition because somebody wants to publish something or study something, but has there been good collaboration here to make sure that we get as much data as we can and enough as much?
Relax your arms.
Sorry.
Very defensive.
Just speaking from your experience.
The best research I have done in my career is through collaboration. There are areas that I'm an expert. There are certain measurements that my lab can do better than any lab, but I cannot do everything. And I'm not an expert in every topic. And especially when you are working on something new or very cool, collaborating with other scientists is the way to go. Like the NASA grant we have to do this work is a collaboration between atmospheric science and satellite remote sensing and geochemistry. We have very different skills, very different tools in our toolbox, but together we can actually do something completely different and new.
And that's what's so important about volcanology, because volcanology is a new science. There's still a lot we don't know about volcanoes, and it's going to need a multidisciplinary approach. So we need all of you guys to work together and to work with lots of different people as well to get to the bottom of what's going on.
Yeah, and you know, like the most papers we can get together, the better it's for everyone. And in the end, what we're here is to try to move our scientific knowledge more, understand the processes better. And is in my opinion, it's not a competition of who published first, it's who published best.
That's very good. One final question, because obviously we're from Tenerife, and one of the things we're looking at is what can we learn from this eruption to put into place in case we have an eruption in Tenerife. Now, there's a couple of aspects to this question, but let's just start with the general question first. Is there anything that you've seen that we could learn from or do differently or would need to bear in mind for a future eruption on an island that's bigger, with a much bigger population?
It's a little bit outside of my expertise, because basically doing an assessment of volcanic hazards is a very difficult field. It also requires an interdisciplinary approach. And we also have the dimension that basically you're dealing with, people's livelihood here. So you also need that dimension that comes from social sciences here. But I think the best volcanic regions can do is to be really prepared. So establishing the areas where people can live, that areas that people should be avoiding. And to some extent, the location where a new cone can start like this are kind of unpredictable. If you look at the island of Tenerife, there are cinder cones everywhere. They're dead, but that doesn't mean that a new one cannot start. And historically, they pop all over the island, and there has been a significant development. So I think it's very smart for regions or countries that are actively in an area that volcanoes can start anywhere, or volcanoes can be active anywhere, to be really aware of this and have a good system. I'm very impressed of what happened here, of the way this emergency has been taken care by the authorities and how well monitored, how well done everything is. But we also need to accept the fact that if you live in a volcanic island, there is a chance that you will deal with an eruption in your lifetime.
Absolutely. And in terms of preparing,
Careful on your feet. Sorry, you're stamping of your feet.
Okay.
yeah, we do have to accept that. And there's a lot of talk about people being resilient. But to my mind, being resilient doesn't mean just accepting something. It means putting measures in place so that you're as prepared as you can be to deal with something happening. So one of the things that strikes me, for example, about Tenerife is that there isn't a hazard map. So people are building houses, but they're not aware of whether one area is more likely or more hazardous than another, whether it's more likely to have an eruption than another. And that brings up all sorts of problems, surely.
Yeah. Again, like I'm in this topic. I'm not the best person, perhaps, to have this conversation. I will think Paco.
Yes.
Or Juan Carlos Carrasero, or
yes.
some, or
Yes.
I don't Juan Carlos.
No, that's fine. Don't
Yeah.
worry. That's fine.
Juan Carlos' brother-in-law.
I'm not here
Yeah.
to put you under any pressure.
Yeah.
It's just I've got questions obviously that I'm interested in, and if you're the right person to answer them, great. If not, we will be speaking to them later. So that's fine. So let's move on.
Yeah. Okay.
In terms of Tenerife, if there was a volcanic eruption, what we are told is the likelihood is that it'll be one of these types of eruptions, which are more sort of effusive, strombolian, and it'll be a question of where it comes out as to whether it'll be more or less of a risk to people living there. However, Tenerife also has a long history of very explosive Plinian and subplinian eruptions.
Yep.
And we haven't had enough science done to know what the likelihood is of one or another type of eruption. Is that science that could be being done right now?
I think so. There is I think enough data that suggests that the volcano that collapsed, called Las Cañadas, produced a lot of these Plinian eruptions that they covered most of the island. Those kind of eruptions are not something to. It's not going to be like this. And then
Sorry, when you say it's not going to be like this, what is it going to be like if it was one of those types of eruptions?
Well, it's an eruption that will cover the whole island.
In what?
A matters of hours to days. It's not the kind of eruption that you can evacuate like a little area. Those are significant. And those are very aggressive too. But they had not been those kind of eruptions in a while. So I think the best plan here will be to do a systematic study and try to get a better idea of how often they happen in the past. But it's a unique actually behavior that Tenerife particularly has, because not all the volcanoes in the Canary Islands, not all the islands, have that kind of phonolithic Plinian eruptions. And then El Teide grew after the landslide of Las Cañadas. El Teide grew there and have produced some historical eruptions too that are non-historical eruptions that are also phonolithic. So the center of the island could produce more aggressive eruptions.
And to put it into context, Montaña Blanca, which is to the side of Teide volcano, was a subplinian eruption, so it didn't cover the whole island. It was a subplinian eruption, but that was, I think, 3,000 years ago.
Yeah.
So it's not as if it was millions of years ago.
Yeah, I think as a scientist, I always need to justify what I do. I think if the authorities can understand a little bit better how important it is to do this kind of studies,
So the authorities need to understand better what an eruption might look like in Tenerife before they can put the right plans into place.
I
Correct?
think this needs to be all over the world.
Yes.
It's not just Tenerife. It's every volcano in this planet needs to be carefully studied, carefully monitored. We need to know their history. We need to reconstruct the past. So what I'm saying is not the authorities. Like, what we need is money. We need funding. We need funding to be ready as a planet for the next Tambora eruption. We need ready as a society to be ready for the next Mount St. Helens or the next, like Teide eruption.
So put that into context. That's brilliant. I need you to put, so that we can be positive and offer solutions in what we're doing. I don't want to just say, oh, this could happen, this would be terrible. This is brilliant what you're saying. So if you could put it into context for me and just say, in Tenerife, we need funding and we should be looking at this. What is it that we need to be doing, studying to understand specifically?
Okay, so what we need to do
So
is...
in Tenerife?
Yeah, in Tenerife, it will be incredibly helpful if we have systematic studies of all these different eruptions, if we can use diffusion clocks to understand how long it takes for them to come to the surface. So when the earthquakes start or something, we have an idea of how much time we have to prepare. Getting ages of all the eruptions will give us a good idea of how often they happen, and understanding the volcano as a system too will help us understand better if the volcano is compressing or is extending, and if the volatiles can come out at a better efficiency. So it may be that we're still going to have phonolytic eruptions, but they're going to be lava flows because they don't have the volatiles.
So in other words, they'll just, the lava will just come out, or they'll just be highly explosive. Can we know that in advance? Can we know what's below?
Not until we invest more resources in research.
So is there a way of knowing what the likelihood is of either just this style of eruption or a very explosive eruption? Is there any science we could be doing right now in Tenerife to know the difference of what the likelihood is?
Yeah, I think we can do more. As I told you before, like if we can date the eruptions, have reconstruct the record, get diffusion clocks and volatile contents, that will give us a much better idea what could potentially happen in the future.
Can you just explain those two last things? Diffusion.
Okay, sorry.
I don't understand
Sorry.
what that means. Yeah.
So diffusion is the property that elements move through materials, and basically we through experiments we can quantify the movement of elements through a mineral. So those experiments have helped us calibrate, and we call it diffusion clocks. Okay, so through experiments we can quantify how fast an element can move through the lattice of a mineral. And when volcanoes erupt, that information gets frozen. So we can take minerals and we can analyze their chemical composition, and we can actually get a time from the reservoir deep in the earth to the surface, how long it takes to come up. So if we can do more diffusion studies, we can have a much better idea from where earthquakes start, from when we see ascending magmas, how long it will take for the volcano to erupt. And therefore, we can prepare better. That's one thing. But basically, what we need to do is invest more in science. We need to invest in volcanology. We need to do more mapping. We need to understand the volcanic record. We need to use geochemical studies, like the diffusion clock studies that I mentioned. We need to understand their volatile contents. That's mostly what my lab is basically focusing on. And if we start putting all those different dimensions together, we'll have a much better idea what the future get us. And also, like, some of the things may be in the scales that are much bigger than the scale of humanity. Like humans have been for as civilization for a few thousand years, and as Homo sapiens for maybe 100,000 years.
But sometimes that's used as an excuse not to invest in science. But here we are in the Canary Islands, and there's an eruption happening.
I think everything is used as an excuse not to invest in science. But when we know that when we invest in science, we can have a much better idea how the world works, and we can do better. If we had not, like, compared to the last eruption of Teneguía, and this eruption, there has been a significant investment in science in Spain. So a week before this eruption happened, I was in my volcanology class, and one of my students that is here with me, Kyle, said the earthquakes are getting shallower and it's more imminent than an eruption is going to happen. A week after that, the volcano erupted. The last time there was information that there may be an eruption because there was a CIA station that provided information that could be related to maybe earthquakes or something. So science and technology, investing in science and technology could help us take care of emergencies better. Like, look, again, this is the magnitude of some of these events are so big that the best we can do is to try to save lives. And we cannot do that if we don't have a much higher investment in science.